This is problem 53 and problem 54 from chapter 15. In these problems, block A has a mass of 5 kilograms and is placed on the smooth triangular block B, having a mass of 30 kilograms. If the system is released from rest, determine the distance B moves from point O when A reaches the bottom. Neglect the size of block A. And in problem 54, we want to solve the same thing, but with a coefficient of kinetic friction between A and B, which is equal to 0.3. We are told to neglect the friction between block B and the horizontal plane. They don't say anything about that in problem 53, but we're going to assume that we're ignoring the friction between block B and the horizontal plane in problem 53 as well. So we have the masses for the two blocks. Block A is released from rest, and we're assuming there's no friction between B and the horizontal plane. We're going to choose our system to be the two blocks. And we have a normal force acting on block B. We have a force of gravity acting downwards. And if there's no friction between the horizontal plane and block B, then there are no forces in the horizontal direction. So I can use my impulse momentum relationship in the horizontal direction. And this is going to be similar to what I did in problem 50. So nothing's moving to begin with. So the initial momentum is equal to 0. And we can say that is the momentum of all of the mass times the velocity of the mass center, and it's at rest to begin with. So this is from problem 50. It's at rest to begin with, so the initial momentum is equal to 0. This means that the location of the center of mass for our system does not change. So in the problem 50, we wrote out the momentum as the sum of the momentum for each object, and then we said we could write the velocity as the change in position over the change in time. We're going to do the same thing here. So the position of the center of mass does not change, which means that at every point along the way, mass A times velocity A plus mass B times velocity B must be equal to 0. And note that A and B are moving in the opposite directions, so the velocities here should have different signs. But we can also say mass A times, we're looking in the horizontal direction, so delta XA over delta T plus mass B times delta XB over delta T is equal to 0. And we can look at whatever time interval we want to, but whatever we choose is going to be the same for block A and for block B, so we can multiply both sides by delta T. And as block A slides downward, block B is going to move in the opposite direction. So by the time A gets to the bottom, the whole wedge has moved to the right. So we have the situation before, the situation afterwards where the whole wedge has moved. And let's call this distance here x. And let's rewrite our equation using x. So we have, let's start with mass B. Started here, ended here, so mass B moved a distance x, so delta XB is x, and it moved in the positive direction. Mass A moved in the negative direction. It started here, it ended here. The distance between this point and this point is 0.5 minus x, but it moved in the negative direction. Or you can say this, if you want delta XA, well, first let's say we have mass A times its initial position, if you're measuring from this point here, is 0.5. Its final position is 0.6, so delta x would be x minus 0.5, which is the same thing that you would get if you used this distance and made it negative, since A went in the negative direction. So now we can take this and we can solve for x. We know mass A is equal to 5, mass B is equal to 30, and so we have 0 is equal to, mass A is 5, so this is 5 times x minus 5 times 0.5 plus mass B is equal to 30. This is 30 times x. We'll bring the 5 times 0.5 over to the other side, and let's call it 2.5 is equal to 5x plus 30x, so that's 35x. So we have x is equal to 2.5 5 divided by 35, which is equal to 0.0714 meters, or you could call that 71.4 millimeters. And this is the answer to problem 53. In problem 54, we are considering what would change if there is friction between block A and block B. But look at the system that we have here. If you had friction between block A and block B, you'd have a force acting on block A, the force of friction acting this way, the force of friction by Newton's third law that A exerts on B would have the same magnitude but pointing in the other direction. These forces are equal and opposite. And if you're looking at the system as a whole, these two would cancel out. So if you have friction between block A and block B, if you're only looking to see what this distance is, it does not matter what the coefficient of friction is. So you would have the same answer for problem 53 as you have for problem 54. So the distance that block B moves does not change, but you can ask yourself whether anything else would change. And that concludes problem 53 and problem 54.